Okay, so this week we are looking at residual plots and correlation. So residual plots, a residual is just the difference between the actual data, so the actual data value, and the predicted data value. Okay, now this goes along with the regression equations that we talked about last week. So when you have a scatter plot and you're trying to determine the best model to use, that regression equation, that either the regression, the line or the parabola, whatever we're trying to fit the data with to best represent it, that's going to be that regression line that we're making. That's what I'm talking about when we're saying actual data versus the predicted data. So how close is our actual data to that either line or parabola that we're drawing through our data? So when we look at this, it says we're given this first scatter plot, right? So they drew a line of best fit. Okay, so our regression equation would have been linear. If you are to make a residual plot, what that's showing is from this equation that we're making, from this regression equation, that is now, we're looking at the residuals to see how far above and how far below the line are the data points. If we choose the right model, the data points will be scattered pretty evenly above and below our residual plot. Okay, so that if we were to average it out, it would be pretty close to zero. Like the points that are above the line would cancel out the points that are below the line. I hope that's making sense. So when you look at your residual plot, you want something that's nice and scattered. So about as many points below as there are above. Now notice this one, there are a few more points above, so maybe they should have taken their regression equation and moved it up just a smidge to get a couple more points below it so that it would have evened out. So what do you notice about the scatter plot? So the scatter plot, I'm going to say it uses the correct model. Okay, this is definitely a linear trend. Now, maybe they should have bumped it up a little bit, but it does use the correct model. Now, what do we notice about our residual plot? Residual plot is scattered. Okay, we've got them above and below, so it's pretty good. Again, it could be a little bit better, but overall it's pretty good. We have points that are above and below. So same thing, when we look at this one, now notice our original scatter plot, it definitely has a parabolic shape, so they fit a quadratic to it. All right, so that's an appropriate fit. So our scatter plot uses correct model. Okay, we used a parabola. We should have used a parabola. So the residual plot, if we look at that, we've got a few above, few below, few above, a few below. So our residual plot is scattered, which is good. Okay, so even though like that looks pretty far below, well, that one looks pretty far above. So those two would cancel each other out. You get what I'm saying? So again, pretty far above, pretty far below. So those two would cancel each other out. That's what we're going for here, is we want to figure out, does our data kind of cancel it out? Really, ultimately, if we were to average them all together, we'd end up with zero. Now let's look at something that does not fit. So this scatter plot right here, if you look at that, if we go up, we go back down. That is definitely a quadratic. It's a parabolic shape. However, they fit a line to the data. Well, that doesn't make sense. Okay, so our scatter plot definitely has the wrong model. And since it has the wrong model, when we look at our residual plot, we notice a shape. So residual plots, shapes are not good. Okay, that means that we fit something linear when we should have had something quadratic. So residual plot, we have a pattern. Okay, pattern, no bueno. So look at our last one. Is this the correct model? Should they have fit something linear to this scatter plot? Well, notice how quickly our data decreases and then it kind of flattens out toward the x-axis. What kind of model should that have been? That should have been an exponential model. That's an exponential decay. Okay, so our scatter plot, again, this scatter plot is using the wrong model. And since it is using the wrong model, our residual plot is not nice and scattered. It has a pattern. No good. Okay, so residual plots, I know most of the time we're looking for a pattern. However, with residual plots, we want it nice and scattered because what that means is that regression equation that we use is a good fit. It's falling in the middle of our data. We've got some above, some below. Okay, that's all I need you guys to know about residual plots. There's a lot more that goes into it, but you'll get more into that when you get into stats in high school. All right, so residual plots, as long as something is a good fit, you have a nice scattered residual plot. If it is not a good fit, if they did not use the correct model, then you're going to end up with a pattern. That's not what you want. Now, another thing with statistics when we're making observations is looking at correlation. Okay, so when we're looking at correlation, the correlation coefficient, which is just R is what represents correlation coefficient, it measures the strength and direction of the linear association between two quantitative variables. Okay, so correlation coefficient, when we're looking at the correlation between things, it's only going to be with linear data. Okay, you're not paying attention to quadratics or exponentials. Correlation, we just look at something linear. We look at how does the x affect the y? Is there a strong or a weak correlation? Now, this correlation coefficient is going to be somewhere between -1 and +1. Okay? So if there's a super strong, if there is a perfect negative correlation, okay? So think about a line with a negative slope. If there is a perfect negative correlation, if those if those dots fall in make a perfect line, again, in real life, not going to happen, but if it's perfect, that is going to be a -1. So the closer something is to a -1, it's like a -9/10, something like that, that is a very strong negative linear relationship. On the other hand, if you've got a perfectly straight line that has a positive slope, then we are going to have a positive correlation coefficient. The stronger it is, the closer it is to a +1. 0 just means there is no relationship. Okay, it is just a hot scattered mess. So again, correlation coefficients, these are not used with a with a residual plot. That's not what we're talking about. We're talking about the scatter plot. Does our scatter plot have a linear pattern? And if it does, how strong is that linear pattern? Okay, so when we look at these examples, I want to look at when I'm talking about my different correlation coefficients. Okay, I want to know, again, we're looking at strength and direction. Strength, meaning is it close? How close is it to either 0 or 1? And then the direction, is it positive or negative? So think slopes. So looking at this one, I have a very strong correlation. Notice. Now, slope, is it going up or down? So we're going down. So this is a strong negative correlation. So when I look at my answer options, it's not perfect. Okay, they don't make a perfect line, but they're very tightly clustered around that line. So a strong negative correlation would be this negative 0.991. Okay, so my other one. Okay, so our trend is definitely negative. It is going down, but it is not super strong. Notice how this is a scatter plot, okay? Our goal is to have stuff that's nice and close together. So it's got a slightly negative, I can see that they're going down, but they're still very spread apart. So let's see this weak negative correlation. Okay. Don't think that one because that's pretty much no correlation at all, which I'm going. So no correlation at all. I'm seeing this middle one. That's just a hot jumbled mess. The fact that they're giving that a negative is just them being nice. All right, so what's our next week? Strong. Okay, so negative 0.547. So again, it is a negative correlation. It's just not very strong at all. I wouldn't have even given it that strong. Okay, so this one, we are going up, so a nice positive correlation. Not super strong, but not crazy weak either. So that, let's see. We've got positive 0.79 and positive 0.99. Okay, so pretty strong, but not super strong. So this one is going to take our 0.79. And then this one is definitely more tightly clustered around that line. So this will be our positive 0.990. Okay. Now, this is usually something that I like to have a nice class discussion, but I don't know how we're going to do that. So just because there is a correlation between two things, so between our x and our y, just because there is a strong correlation, that does not imply causation. Okay, so let's take this one right here. This is a pretty strong positive correlation. Now let's put an example to it. So let's say our x-axis is temperature and our y-axis is ice cream sales. Okay, so this is saying as our temperature rises, ice cream sales are also increasing. All right, that makes sense. However, does a rise in temperature cause you to buy ice cream? Does it cause you to buy ice cream? No. Now, is it probably going to influence you to want to buy something cold to cool off? Absolutely. But it does not cause you to buy ice cream. Okay? If you're sitting here going, are you sure? Well, let me give you another example. What if on the x-axis was smoking and on the y-axis was lung cancer? So the more you smoke, the more likely you are to have lung cancer. Is that a causal relationship? Does smoking cause lung cancer? Yes. Okay, so hopefully that kind of clarified. So just because there is correlation, it does not imply causation. There's not necessarily a causal relationship. So we can have a relationship, there can be correlation, but one thing doesn't necessarily cause the other. So that is one thing to think about when you're looking at real world examples of these. Okay, so I hope you guys have an awesome week. Oh, there's my nerdy little cartoon. Maybe you'll get it now. Okay, so have a good one.